Oh, is your name on it? Yeah, everyone should be able to finally register.
I'm about to right now. I could do it in like 5 minutes.
Thank you.
Just got a lot of class or something.
Are you gonna do bowling?
I don't think it counts for that. I had online classes where you did math, coding, statistics, chemistry. Oh, dude, that's the one where my board is like so big.
Oh, did you see this line card as soon as you understand?
No, I was going through in the.
Oh, I think it's the Stewart though. You can go through the Stewart's parking lot. And that's like the front door. And then I think they start
Yes, it's hard, it's difficult.
Same spot.
I don't know, maybe it's way too soon about that.
Just in my degree audit.
For what? You like good lugs?
All right, let's go ahead and get started. Any questions about anything before we begin?
all of it.
All of it?
It's very
Are there any specific questions or
Could you do an example of an ionic equation?
There you go.
of the like net ionic equation? So let's do that.
Unless everybody else is clear on that and I'm the only one that's not.
No, I'm sure. Oh, so before we do that, did I give y'all solubility rules? It probably looked different than this one, but I thought I had, no? It looks different than this. This is another form, but you know the internet these days, like I can't find the perfect one that I like.
You use common polyatomic forms.
Uh-oh. I'm gonna have to print out more. So I have some copies of the solubility rules. It would have been like,
This one,
yeah, I think that's it.
it's 2 pages.
Yeah, that one. Like it, yeah, that's the overkill one.
Perfect.
Yeah, so it was 2 pages, and it was kind of complicated looking, but I gave, since you're upper level chemistry, I gave you the very complete one. I have 16 copies of the, it's still good, it's just concise, and there are probably like exceptions that may not be on here. So you can grab that, so that can help clarify. And so let's practice an equation. So let's do, so calcium chloride plus sodium phosphate. So 2 solutions of this are mixed together. So what would be the precipitate, or actually, will there be a reaction? If so, what's the precipitate? And then write the net ionic equation. So I'll give you a few minutes to at least get started, and we'll go over it. So you keep them together since they're the polyatomic, and that's how you kind of double check yourself, is if you see this PO4, look at your polyatomic sheet, then you see, okay, I find phosphate that's 3 minus, and that makes sense because there's 3 sodium, so then you know that's what you're looking at, sodium phosphate. So first tell me, so what are the 2 possible products that we could have made? So I heard sodium chloride, and then the other one I think I heard CaPO4, but then,
But you would do like 3, right, and then 4.
yeah, excellent. And so you could do, right, scratch work on the side, so how we got there. So we know that our new combination by our double displacement reaction would be calcium and phosphate. Calcium in the 2+ oxidation state. Phosphate is all the polyatomic -3. And then easiest way was just like that. So with our swap trick for our neutral molecule. All right, so excellent. So we have our 2 possible products. And then the next question is, okay, of these 2, are any of them insoluble? So then, yeah, so calcium phosphate, exactly. So you found that that was insoluble, so you could put a little solid there. And then sodium chloride's aqueous. And so to write the net ionic equation, we can formally separate it all out. And so I'm just going to start with ions in solution disassociating, and probably should balance it, but we could balance it at the end too. And so this disassociates, so you make 3 sodiums, polyatomic stays together. And then, of course, the calcium phosphate, since y'all determined that it was a precipitate, it stays as our solid. And then we can cross out our spectator ions, so our spectator ions didn't do anything. They wouldn't drop out of solution. And so now at the end, we can balance, so we need 3 equivalents of our calcium ion plus 2 equivalents of phosphate to give us calcium phosphate.
This is gonna be on quiz today.
There will be 1 question like that. We could do another practice. So let's do another one.
Could you also maybe just explain the spectator ions, or what that means?
So it goes back to like the way I like thinking about it. So you can go through, of course, this formal process of canceling them out. But what we're really thinking is, again, ions in a beaker. So calcium is floating around, your chlorine's floating around, right? Sodium and phosphate. So all those are floating around. And so you're just coming up with your possible combinations. And so, of course, sodium and chlorine, right, they can look at each other again, but we said they were aqueous, so they're just going to go back in solution, not do anything. And then, oh, I forgot to draw the chlorines in there. Oh, no, who am I missing? Oh, no, I have everybody. I'm just crazy. And then, so same thing, so sodium and phosphate, that's what we had originally. So same thing, they'll look at each other again, but then since it's aqueous, they'll just disassociate again. So that's what we ultimately mean by spectator, is that they are always in solution, always an ion. But then, again, we can, yeah, they just,
They're not productive, they're not.
yeah. So let's look at two more scenarios, actually. So let's just do another practice first of what you might have on the quiz. So silver nitrate and lithium sulfide. And I should have said aqueous solutions of silver nitrate and lithium sulfide are mixed together. And a precipitate forms. So what is that precipitate? So what do we get for this one? So what's the formula for silver nitrate, first of all? So AgNO3. And what's lithium sulfide? So try.
Oops.
Li2S. And then, so what are our two possible products? So lithium nitrate, and I heard someone else say silver. So silver sulfide. And what's the formula for silver sulfide? Yeah, Ag2, since silver is usually in the 1 plus. And let's balance it this time. I think it's balanced. And so which one is a precipitate? Lithium nitrate? So the silver one should be insoluble. I don't know if the abbreviated rules for those have. Yeah, so you're usually insoluble. I'm just making sure your rules say that. And so this one would be the solid. And so you could, just jump to the net ionic equation if you see it. So just write your silver cation plus your sulfide anion gives you silver sulfide. Or we can go through the process more formally of splitting it up into everything first. So just writing out all our ions. So all these are aqueous. So notice your lithium sulfide. So this is soluble. And so now cross out our spectator ions. So our lithium, and we're just crossing out again what's the same on each side, and 2 nitrates, and then leaving us with our net ionic equation. So 2 silver plus 1 sulfide gives us our silver sulfide. So let's try one more example. So what is the product, and I'll see, if any, if aqueous solutions of potassium chloride and magnesium acetate are mixed? So what do we get for this one?
Would it be potassium acetate and magnesium chloride?
So our two products, so let's write out. So potassium chloride plus magnesium acetate. And you said magnesium chloride, oops, plus, you said potassium acetate. So these are our two potential products. So which one is insoluble, if any? So none of them, right? So all chloride salts are soluble. There were some exceptions, but magnesium's not on there. Yeah.
Why did you write two O's and then put a two next to it?
Yeah.
Oh, because the acetate, this whole thing, has a -1 charge. And then magnesium's the 2+, so then I put a bracket around the whole acetate and put my subscript there.
But isn't acetate just one?
Oh, I just wrote it out, so you could write CH3O2.
Oh, okay. Yes.
And
That's right.
I just wrote it out reflective of the structure,
Oh, I see, okay.
because acetate is carbon double bond O, the negative charge.
So our, the sheet that you gave us last week has it as C2H3O2?
Yeah, so,
No. Oh. She just
Oh.
shoved it to, that's what we were talking about.
oh, my bad. Yeah, I left, it should be a 2 there, yeah. So they're the same thing. So there are two carbons here, right? I just dropped it there, but here I just wrote it out.
So you confused us already.
Yeah, I'm sorry. The acetate is one of those ones that I warned you about for this reason, because,
One of the papers
No,
you
no,
gave
no.
us is wrong.
oh, it is?
This one doesn't have the two next to the C.
Are you sure it does not have a C over here?
Where?
I have to look at, here I can look at your chart.
Oh, it does.
Yeah, it's confusing because it's written both ways. So these are both acetate. And this is acetate, so this is a carbon, right, with 3 hydrogens on it.
She's like, please check all your documents I handed you.
I know, now I'm scared. You never know what you find on the internet. So. If you find it on the internet, it's true. All right, so acetate, acetate. So we determine magnesium chloride, right? Aqueous. So chloride, the magnesium was not one of our exceptions. So same thing with acetate. I think all acetate salts are soluble. Perhaps we could find some exception, but definitely not potassium. And so in this case, you'd actually want to write no reaction. So they would all just be ions in solution, staring at each other, not doing anything.
So technically, would it be magnesium chloride and potassium acetate and also potassium chloride and magnesium acetate? Like,
Yeah, because they're not really doing anything, yeah. And then I think if you like dried it out, you'd probably get, yeah, a weird mixture, because I'm not sure if they'd be like, forming together at that point. Because you have to boil off all the water, and like what salts would be left behind? Like probably a mixture then of all those combinations. Because, and at that point, maybe you could, so then we'd start getting into like second and third quarter stuff, like really looking at the solubility, because that's where that would start into play. So we would have to look, right now we're looking at everything as fully soluble, but there's such techniques as like, I just blanked on what the technique is called, but it's like selective solubility. And so you can take like it works well with hydroxide salts like magnesium hydroxide and calcium hydroxide. They have different solubilities, so you can purify water by getting one of them to precipitate out first as you increase the concentration. So naming acids. Oops. So we have, so like HNO3, so it comes from nitric, or sorry, it's from nitrate, right, your nitrate ion. But a lot of them just have like weird names too, because this one doesn't really follow a pattern. Because this one is just like nitric acid. And then so HCl, so hydrochloric acid. HF would be the same thing, hydrofluoric. And so H2SO4, that's sulfuric acid. And so this is the higher order oxygen, right, sulfate, related to our sulfate. And then so H2SO3, that's from, oh, sorry, that's 2 minus, so sulfite. And so that makes it sulfurous acid. So the higher oxygen has the ic, the lower one has the O, so sulfurous acid.
So, the
H2C2O4. I have to remind myself what C2O4 is. So if it's oxalate, I'm guessing it would be oxalic acid. Yeah. So once again, you have that 8 ending. So then oxalic going to the ic acid. Yeah.
So anything with magnesium in it is probably gonna be an acid.
Yeah. So there's also, we can go back to acetate. So H and then C2H3O2 for the other form, just to confuse y'all. So acetate, so then this becomes acetic acid. So again, changing that 8 to ic. Do you have benzoate on your polyatomic? So benzoate also works, so it follows the same pattern. Benzoate, so then it would be benzoic acid. So H, I have to look at the formula. So H2 and C7H5. Does benzoate have a -1 charge? Oh, sorry, I put too many hydrogens. I don't use benzoate, so I don't remember. There we go. You could go crazy. So another one. So this is phenol. And so you could also have phenolic acid. Phenolic acid. Oh. And then the acid. So this is a phenol group, but then to make it an acid, it has to have a carboxylic acid, so it would look like that. This is more like organic naming now, but you can kind of see it still follows the same general pattern. So this is phenolic acid based off of the phenol group. Any other acids that came up? Oh, that's just hydrobromic. So following with the same pattern, hydrochloric, hydrofluoric. More questions?
Also for over, writing the formula for the name of the compounds, like we're using, ammonium chloride.
So with our polyatomics, so let's do some polyatomic naming. So let's start with the one you asked. So we'll do ammonium carbonate. Let me put some more on there. Do we have answers for all of these? So what do we get for ammonium carbonate?
NH4CO3.
And then do we need some subscript somewhere? So NH4 so ammonium has that 1 plus for the polyatomic carbonate, should be -2, so you can still do your little swap trick and figure out I need 2 equivalents of ammonium. What about iron 3 sulfate? Fe2, SO4, 3, so that looks good. So sulfate is -2. And then so we can double check. So -2 times 3, -6. 3 times 2 is +6, so that all works out. And then chromium acetate, or chromium 6 acetate.
CR, C2, or H3O2, and then 6.
Exactly. Oops. Do we feel okay about naming? Any other requests? All right, well, let's go over, so not to throw another assignment at you, but I wanted to do one last assignment before the end of the quarter. So I wanted to go over it, and then I'll post this on Blackboard probably today, probably like on the announcements, and put this somewhere so you can find it. And so, have you all done a journal article review before in other classes, or? Yeah, so it's the same sort of thing. And so the goal is to get you thinking about what topic you might want to do for your research paper. So I don't know if I mentioned it in the beginning of the class. I think I did, but basically in winter quarter, we're going to be at least writing a rough draft of a paper, so that'll be due at the end of winter quarter. And so that's going to be more for completion graded, and then I'm going to have spring break to kind of go through it, edit it, and then give you some feedback, and then you'll get a chance to rewrite it all over spring quarter, and then you'll have your final paper and then a presentation at the very end of spring quarter. And so last year it was a lot of fun. Everybody got to pick a different topic. And so what we're going to do today is you're just going to do a journal article. Well, not today, but it'll be due by the end of the quarter, so December 2nd. And so you'll be asked to find a journal article in some topic you might be interested in. So a lot of people, either pick like energy or drugs, or you can pick anything as long as it's, somewhat chemistry related. So it can be engineering, designing your materials, whatever, related to whatever you're interested in. So if you have more of a biological interest, related to medicine or how processes work in the body, but you're just trying to find some topic. And then so you're going to do just a short review of the article that tries to highlight the importance, why would you want to do this? What is the experiment trying to show? How does it add knowledge to add to the body of knowledge? And so you're asked to select a research paper, again, related to whatever topic. And so this should be a primary source. And so we've been looking at these CHEM ed articles, and you're welcome to select one of those if, right now you can't think of a topic and want some time. So you can go back to one that we've read and write a review on that. And so you should just write a one-page summary, again, just highlighting the relevance. And if you need help getting a paper, so I know a lot of them are behind paywalls, so I can help you with that. And so if you send me a link, hey, I wanted to at least look at this paper, I can send that to you as well. And so again, some topics, and this is obviously not a limit, just try to give you some inspiration. So people did like energy, and you can either look at, really specifics or try to compare them all. So lots to think about. And then pharmaceuticals could be anything for any sort of drug development, natural product synthesis. Um, this was a really popular topic last quarter, nootropics, or last year, I mean, and antidepressants. But again, there's so many pharmaceuticals that are not these, so like high blood pressure medication, all sorts of things. There's so much money in this. Then agriculture, so you could think about anything from pesticides, fertilizer production, and then of course there's tons of research in this area of CO2 capture or nitrogen, small molecule activation. So you can think about how to make any of these materials, so paints, new like carbon nanotubes to make new materials like for bikes or for space, so paints, lubricants, anything. So obviously there's no limit. And then I'll also include, so in addition, so we'll practice using the ACS format. So this is what like JAX uses in their journal article. And I put a link to this citation generator, so it helps you generate it, but it also has really clear examples of how you should lay it out. And then I'll add to this a example. And so this is just some example of what a review might look like. And this one's very colloquially written, and obviously this is written by that same guy, I think I mentioned him before, Derek Lowe, like Things I Will Not Work With. So he writes professionally, so it's really well written, but it at least gives you an idea, it's at least telling you why is this important, because it's really hard to control these stereoisomers, so just giving you some background of why this research paper is cool that he's referring to. And again, just giving some background. Obviously, this is longer than what I'm asking for, but at least gives you a general idea of what you're trying to write. So just some sort of summary, why it's cool, where the research is going, and why we care. So does that sound relatively straightforward? Okay, so I will post this to Blackboard. And then grade-wise, it'll probably be, Dorothy and I decided we'll probably just make it work like a quiz grade. And we'll probably drop a quiz anyways, but that'll give you more cushion for your quiz grades and kind of help you out. And it won't like super penalize anybody. But it should be a easy A for that assignment. All right, any other questions? Now we're ready to begin. After we ate up half of the lecture, but that's fine. That's good. Keep the questions coming, because gotta have a good foundation in chemistry.
So for that article, we just have to cite what article we got it from.
Yeah. So you'll just, for your citation, it'll just be like the one article. So later for your research paper, you'll have like more sources, but for this one, you're just practicing citing the one article in that ACS format, so I can check it like, yes, you did it correct, and then when you do, the 5 or however many sources you have, they'll all be correct.
So you want like summary, your name, everything like that, and summary, and then that kind of thing.
Yeah, so you'll just have, your name, and then your, 1 to 2 paragraphs, short summary, and then just a citation at the bottom. And you could do like a formal like references, and then just have the one, That's how it'd be set up. Other questions?
Can we just hand that in paper form?
Yeah, or electronic, whatever's easier for y'all. All right, so now let's look at reaction stoichiometry. And so our stoichiometry, so when we get our balanced equation, so this is really our recipe, right? So you can think about it just like when you bake, you have some sort of ratio of flour to sugar to eggs or all that good stuff, non-egg or egg substitute. But basically, trying to be inclusive here. But basically, right, this is our recipe. What ratios do we need to add all our ingredients in, and then how much are we going to get out, right? How many cakes are we going to bake or whatever we're interested in, so we can scale it, of course, up and down appropriately. And so our coefficients in our chemical reaction, of course, specify the relative amounts in moles of each of the substances involved. And so here we have our balanced equation. So of course, right, we have the same number of atoms on each side. But then what this is also saying, so we can look at it at the individual level. So 2 molecules of octane react with 25 molecules of oxygen to give us 16 molecules of CO2 and 18 molecules of water. Or we can scale it up to the moles. So, right, 2 moles of octane react with 25 moles of oxygen to give us 16 moles of CO2 and 18 moles of water. But then, of course, you're not limited by that. So you could scale it by any factor, so times, 2 to give us our 4 to 50 to 32 to 36 ratio, times 10. Obviously you could go on and on here. So it's just our ratio.
I'm gonna ask a stupid question. How do you get, I mean, on one side it's 27, but then on the other side it's 34. So how do you get more? Or is that not important?
Oh, like more moles? Because you care more about the atoms, right?
Okay.
So the amount of moles doesn't matter, like,
Okay.
because we've seen that with like our combination reactions too. Because you can start off with like 2 moles and then just make like 1 mole of something. It just kind of depends. But yeah, but the atoms should be the same though.
Okay.
And so now let's think about making s'mores. And so I have out this recipe here. And so I added in their molecular weights. And so if you can do s'mores, you can do chemicals. So that's what I always say. And people do wonderfully on the s'mores. And then as soon as we throw the chemical names on them, everything goes out the window for some reason. And so now we have our formula. So 2 graham crackers. So again, just think of that. That could be some crazy polyatomic. It doesn't matter. We just care about our ratios. And then the other thing we just care about is getting our molecular weight. And so in this case, I gave it to you. So the molecular weight of a graham cracker is 55 grams. And then we add 1 equivalent of a jumbo marshmallow, that's 76 grams. And then 3 pieces of chocolate. And each of those has a molecular weight of 15 grams per mole. And then that gives us 1 s'more. And so now let's start with kind of the first type of question you would see. So if I want to make 10 s'mores, how many chocolates do I need? So I heard the answer, so you did it super fast. And so 30. But let's kind of slow it down for a second. So again, when the numbers get hard, you'll know what to do. So this one was easy. So all you did was you have your mole-mole ratio, your conversion factor. So we have 10 s'mores. Then we can write our conversion factor, again, just using our mole-mole ratios. So 1 s'more requires 3 chocolates. So again, doesn't matter what the number is, could get crazy. So that's our conversion factor. Now we can just set it up by dimensional analysis. And then so that gives us to our 30 pieces. And so let's try another one. So now if we have 32 graham crackers, how many chocolate pieces do I need? What'd you say, 48? So everyone got 48, and so again, I'll write it out explicitly. It seems easy now, but for some reason, once those numbers get different, then things start to break down. So 32, and then you just set up your ratio. So now we're comparing our coefficients. So again, we're just looking at our coefficients. So 2 graham crackers to 3 chocolate pieces. So set that up. So your 2 goes on bottom. So grams crackers will cancel. 3 chocolates on top. And then you do the math. So 32 divided by 2, 16 times 3, so 48 pieces. And so now let's look at the next type of problem that you would have. So we don't often give quantities of chemicals in moles, unfortunately. So usually, you have your bottle, dump it out, see what's in there. And so in this case, if we have 543 grams of marshmallows, so how many s'mores can we make then, assuming that we have excess of the other reagents? I'll zoom out for a second so you can get your molecular weight. So did we get an answer yet? So let's hear it, or walk me through what we need to do, or so walk me through. So we have 543 grams. So what do I need to do first? So divide. So essentially we need to find our moles. So then we'd calculate our molecular weight, or in this case, of course, we have to take what's provided. So 1 mole then of marshmallow. And so now, I like to say once we're at our moles, we are at our safe space. And so once you are at moles, you can compare mole-mole ratios. And so we need to compare, so we have a 1-to-1 marshmallow to s'more. So 1 marsh gives me 1 s'more. So how many s'mores can I make?
7.
So 7. So the next type of problem you'll see in chemistry is what's called a limiting reagent problem. And so essentially you kind of have to do this now 3 times for every reagent. And so it asks, you have 430 grams of crackers, 375 grams of marshmallows, and 250 grams of chocolate. So what is the limiting reagent? How many s'mores can I make? So hopefully, can you read that? Okay, zoom in here. Here, I'll just repaste it, that's easier. Oops. We get answers. So let's at least start. So I'll do the graham crackers first. So I have to divide by my molecular weight. And I'll do my ratio. So 2 graham crackers gives me 1 s'more. So graham cracker on bottom, s'more on top. So how many s'mores did we say our 430 grams of graham crackers could give us? So 7. Oh, 7? No, you probably round down, but did we get 3.9? It should be 3.9 because it was 7.8 graham crackers, but then we had that 1-to-2 ratio. So 3.9, or you can say 3 s'mores.
Would the graham cracker be your maybe?
So we have to see. So I didn't do the other ones. So walk me through. So, and we do the marshmallow. So divide by 76. But then they're in a 1-to-1 ratio. So how many s'mores do we get? So here a 4. So 4.9 or 4. And the last one, so 250 grams of chocolate divided by my molecular weight. Then this one's a 3-to-1 ratio, so 1 goes on top for s'more, 3 on bottom. So how many s'mores do we get for this one? So I hear a 5. Oops. So other people got, so about 5 s'mores. I guess I could punch it in. So 250 divided by 45. So 5.5. And so yes, indeed, it was our graham cracker that is our limiting reagent there. All right, so now, if we do this practice, you should nail it, right? So this is obviously an old quiz I gave in the past, and people bombed it surprisingly. So let's go through it for practice. So start with the first part. So we're looking at the Haber-Bosch process. So of course I'm a fan of this process, really important. And so we're given a balanced chemical equation. And so let's just start with what we need to probably do our stoichiometry. So what's our molecular weight of H2, N2, and ammonia? So what do we get? So what's the mass of H2? 2.016. So it could be different with rounding. Molecular weight of N2? 28.014. Again, 28's fine, or whatever. Minor discrepancies. Then ammonia? 17.031 grams per mole. And so now, just trying to have this equation. N2 plus 3H2. All right. So now let's answer these next two questions. So if we have 4 moles of H2, how many moles of nitrogen do you need to react? If you have 2 moles of nitrogen, how many moles of ammonia will you produce? So what do we get for number 4 here? So we have 4 moles of H2. So how many moles of N2 do we need? 3. So we set up our mole-mole ratio. And then, so H2 needs to go on bottom. And I'm just comparing 3 to 1. And so what do we get? So 1.33 moles. What about 5 here? So if we have 2 moles of N2, how many moles of ammonia will we produce? So what's the answer? So 4, so good. So we set up right there in a 1 to 2 ratio. Nitrogen goes on bottom to cancel. 2 ammonia on top, so our 4 moles of ammonia. So just replace these with like graham crackers and s'mores if you need to help you. That's where that makes the stoichiometry friendlier for some reason. All right, so now let's try the next 2 types of questions. And I'll rewrite. So H2 plus N2 gives us ammonia. So now, number 6, if you have 20 grams of nitrogen, how many moles do you need to fully react? And then number 7, if you have 20 grams of hydrogen, how many moles of nitrogen? So let's start with 6. So we have 20 grams of nitrogen, and then what do I need to do with this? So divided by, what do I need to divide it by? What, moles of hydrogen? Well, before we, because we can't compare, because we're in grams right now, right? Yeah, so we need to divide by the molecular weight of N2 first, before we get to our mole ratio with hydrogen. So divide by, so 28.014 grams per mole. So now we're at moles. So now this step brings us to moles of nitrogen. And so now we can do our mole ratio. So looking, so we have a 3-to-1 hydrogen to nitrogen ratio. So moles of nitrogen is on top currently. So now it's going to go on bottom times 3. So then that gives us moles of H2. And so what do we get? Punch this in. Tell me. So I see some nods. So 2.14 moles of H2. And so now let's do the second question. So now we have 20 grams of hydrogen. How many moles of nitrogen? So what do I need to do? So 20 grams of hydrogen. So yeah, divide by molecular weight of hydrogen, since we're in grams of hydrogen. So let's divide by hydrogen, so 2.0, what number do we want to use? 2.016, we'll use that number. Grams per mole of H2. So that cancels, and then we need to use our ratio. So how many moles do we need? So nitrogen goes on bottom, so 3H2 times 1N2. Oops. So do we get something like 3.3? No, that's moles of, so 3.31 moles of N2. And so now looking at these two, assuming that we have 20 grams of nitrogen and 20 grams of hydrogen, which one's our limiting reagent? You might have to go back and do a little bit of math. And it might help you, so you could calculate, well, how many moles is 20 grams of nitrogen versus how many moles is 20 grams of hydrogen? Then that would kind of help you compare these two results. So how many moles of nitrogen do we have? So 0.7 moles, or roughly, of nitrogen. And then how many moles of hydrogen do we have? So about 9 moles, or probably like, what, 9.9 or, so 9.9 moles of hydrogen. So now comparing this, well, if I had 20 grams of nitrogen, I only needed 2.14 moles of hydrogen. We have 9.9. But then looking at the reverse, well, if we have 20 grams of hydrogen, I need 3.3 moles, but we only have 0.7 moles of N2. So who is our limiting reagent? So nitrogen. And so now, kind of running out of time, but let's see if we can do these last two really quickly. So using our limiting reagent, so our 20 grams of nitrogen, how many grams of ammonia is produced? And then once you do 9, you can do 10. So if you recovered 4.20 grams, what's your percent yield? And percent yield, don't forget, is just actual or theoretical. And of course, theoretical assumes 100% yield perfect conditions with our stoichiometry. And then times 100 to get a decimal, or a percentage, I mean. Yeah, so this is, so in the interest of time, we'll go over it. So just starting, so we had 20 grams of our nitrogen divided by our molecular weight like we've done before. Then looking at our equation, so nitrogen and ammonia are in a 1:2 ratio. So ammonia goes on top. So times 2. And then we have to multiply it by our 17 grams then. So I just rounded, but it came from up here, the 17.031. And so that's grams per mole. That cancels. And so you should get roughly 24 grams for your theoretical yield. And then not a very good percent yield today, so 4.2 divided by 24. And so I get like a 17% yield. All right, we are out of an overtime. So everyone take your 10-minute break and then we'll come back and do the quiz. No, not this stuff, just like the drawing Lewis dot structures, oxidizing reduction stuff, like identifying reactions.